Hey guys, welcome to video 76. Today we're going to start a series of topics that I think you're really going to enjoy. It's the analysis and design of transformer coupled power amplifiers. We're going to begin with an analysis of the single-ended Class A transformer coupled amplifier. The typical circuit is shown here on the left. It's a common cathode using cathode feedback biasing and a fully bypassed cathode resistor. And because this is a Class A amplifier, we're going to have a substantial amount of plate current flowing. We're going to try and center the Q point on our AC load line, and that plate current is flowing through the primary of the transformer, so T1 is going to be a transformer with an air gap in the core. These transformers are designed specifically for use in single-ended Class A amplifiers. Now to the right here we've got the DC equivalent of our circuit, and notice that there's no resistance in the plate side of the circuit. That's because we're going to assume that the DC resistance of the primary winding is negligible. That's almost always a valid assumption, and this circuit is relatively easy to analyze. We would just use the normal techniques that we developed in previous videos. Now if we move over to the right, there are a few equations I just want to mention some things about. These are related to the DC analysis. Starting here, IPQ, well, we're going to determine that the way we always have for the circuits we've looked at previously. No mystery there. VPKQ, the voltage from plate to cathode at the Q point. Technically, it's VPP minus IPQ times RK, but normally we're going to assume that it's just VPP because the drop across RK is not that large compared to VPP, and it simplifies the analysis for reasons we'll understand later. And finally, we haven't talked about PDQ much, that is the dissipation of the tube at the Q point, but just like transistors, PDQ equals VPKQ times IPQ. And as far as the DC load line goes, VPK cutoff again is equal to VPP. But the plate saturation current is approximately VPP over RK, which is normally a very, very large value because RK is typically not that large. It might be a couple thousand ohms at the most. Typically it's going to be in the hundreds of ohms, and if we're dealing with a power supply that's hundreds of volts, that means our IPSat value is huge, and if we try to plot the DC load line, it's going to be almost vertical. Now we'll talk about the ramifications of this a little bit later, but it's something to keep in mind that's easy to understand at this point. Now, a few general comments related to the things we're going to be talking about. The maximum theoretical efficiency of a capacitively coupled Class A single-ended amplifier is 25%. We talked about this a lot back in video 36 in relation to transistors. The same theory applies to vacuum tubes, although we do have a little bit of added inefficiency because we have a heater here, but we're not worried about that right now. The maximum theoretical efficiency of a transformer-coupled Class A single-ended amplifier is 50%. So right here we have a good reason to use transformer coupling. It doubles our maximum possible efficiency. Of course, the trade-off is that coupling transformers in power amplifiers tend to be large, heavy, and expensive, but they're a necessity here, so it's just something we have to live with. Now, the maximum theoretical power output from a transformer-coupled Class A single-ended amplifier is PDQ over 2. So if this tube was dissipating 10 watts at the Q point, the maximum theoretical power we could get to our load here is 5 watts. That's because the amplifier is 50% efficient. Now, in practice, we're always going to be somewhat less than 50% efficient, but we'll shoot for that. Again, to reiterate, the DC load line is really steep, and it's almost impossible to plot it on the typical plate curves that we'll be working with. And most of the time, to reiterate, we're going to assume VPKQ is about equal to VPP. If we don't make this assumption, because we can't plot the DC load line, we'd have to resort to some iterative techniques to find the Q point, and either that or solve some simultaneous equations, some of which are nonlinear. Not fun. We're not going to do that. So we're going to make this approximation. All right, now let's go on over to the next page and take a look at what's involved with the AC analysis of this amplifier. Now, we see the AC equivalent for this amplifier is really pretty simple, and down below I have the transconductance model for the small signal analysis just for reference purposes. Now, over here, let's take a look at these equations. R prime K, the AC equivalent cathode resistance, is 0 because we're fully bypassing the cathode resistor. R prime L is the reflected load resistance. We derived this in the previous video. It's equal to RL times the turns ratio squared. R prime P is the small signal AC model resistance. That's the dynamic plate resistance of our tube in parallel with the reflected load resistance. Now, the next equation I have here is A prime V. That is the apparent voltage gain, which is transconductance times R prime P. And I threw the prime on here because it's not really the voltage gain of the amplifier. It's the gain of the plate relative to the grid. But remember, we're going through a transformer here, so to get the actual voltage gain, it's A prime V times the reciprocal of the turns ratio. Usually this transformer is going to be stepping down, so we're going to get a much lower voltage gain overall from the amplifier than from the tube itself from plate to grid. Moving on over to this next red box, we've got the equations for the endpoints of the AC load line. These are the same equations we've been using all along, so there's really nothing new here. Down below in the yellow box, I've solved the reflected load resistance equation for the turns ratio, and this is useful because transformer manufacturers don't give you the turns ratio. They give you the impedance ratio, that is the reflected load resistance for a given load, and you have to solve it for the turns ratio, and that's what I've done here. That's useful for determining the overall voltage gain and so on, as we can see over here on this left-hand side. Now, when we're using transformer coupling, something can happen that's really pretty cool and maybe unexpected, and that is it's possible for VPK cutoff to be larger than the power supply voltage. So if we had a 100 volt power supply on this circuit, it's possible for us to have a VPK cutoff of 200 volts or even more. This can't happen when you're using capacitive coupling. VPK cutoff is always going to be less than or equal to VPP, but in this case we can get a VPK cutoff that's greater than VPP. Now, it's pretty easy to understand how this can happen if we come up and look at our equations for a second. Remember, VPK cutoff is VPKQ plus IPQ times R prime L. VPKQ for this circuit is usually VPP. It's the supply voltage, and because R prime L can be very large, it's equal to NP over NS squared times RL. This term can be very large as well. So overall, that can give us a pretty big value for VPK cutoff. Now, again, because we're usually dealing with a step-down transformer from the tube to our load, we're going to step down our voltage gain as well, and typically for this kind of circuit, the overall gain is going to be less than 10. Sometimes it's even less than 1. But the thing to keep in mind here is that we're not necessarily after a lot of voltage gain from a power amplifier. We want lots of power gain, and that's what we're going to get from this circuit. And one more thing I'd like to go over that's a bit of review we haven't talked about for a long time is the relationship between maximum power or peak power and RMS power. For a sinusoidal voltage, RMS power is equal to the peak or maximum power divided by 2. We talked about this back in video 36 as well. And for just a little bit of review of what is in that video, here are some of the equations and so on that we dealt with related to a transistor, but it also applies to vacuum tubes. And I'm not going to go through this again, so if you want to take a look at this, here's a summary. Go back to video 36 and you can see the full deal. Okay, now The best way to internalize all this and kind of wrap your head around it is just to go and do a problem. So let's go on over to the next page and work a practical problem. Here's the circuit we're going to work with. Let's start at the top and work our way down and see what we got going here. We've got a 250 volt power supply, and our output transformer has a turns ratio of 32 to 1. We're driving an 8 ohm loudspeaker. Now the tube we're using is a 6V6, and since we've connected the screen grid to the plate, it acts like a triode. Internally, the suppressor grid is connected to the cathode, so we don't have to worry about showing that here. Our cathode resistor is fully bypassed, and over here on the right we've got the plate curves for the 6V6 when it's connected up as a triode. Alright, why don't we start our analysis by finding R prime L, the reflected load resistance, and that's R prime L equals RL times NP over NS squared. So we've got 8 ohms times 32 squared, and that works out to be about 8.2 k ohms. Now let's find our small signal plate resistance, R prime P. That's equal to R prime L in parallel with little rp. We don't have little rp listed here, but I've got the data sheet for the 6V6, so let's pull that up. And if we come down a little ways, let's see, we want to make sure we don't accidentally use the pentode characteristics. Those are the first ones listed here. So let's keep going down. And here we have the triode connection parameters for a plate voltage of 250 volts. We've got an amplification factor, mu 9.8. The plate resistance is 1,960 ohms, and our transconductance is 5,000 micromhos, or 5 millimhos. All right, so I'm going to carry these values up to the schematic and write them down. And here's what we've got. Our mu is equal to 9.8. That's not very high. We're going to have a voltage gain for the tube less than that here. Transconductance was 5 millimhos, and our little RP was 1960 ohms. All right, so let's come back over here. R prime P is equal to R prime L in parallel with little rp, so we've got 8.2 k in parallel with 1.96 k, and that works out to be about 1.6 k ohms. Now what I'm going to do next is determine the ends of my DC load line. I'm not going to plot it, and you'll see why in a minute, but let's start with VPK cutoff, and that's simply VPP, which is 250 volts. IP sat is VPP over RK. So we've got 250 volts divided by 560 ohms, which gives us 446 milliamps for IP sat, and that's going to be way up here in space somewhere. So our DC load line would go from 250 up almost vertically. So that's why we're not going to bother plotting it. It's just not feasible here. Now, even though I don't have a DC load line or the bias line plotted yet, I can still approximate VPKQ as being VPP, which is 250 volts, and that's because we've got such a small drop across RK relative to the power supply. This is a valid approximation. Next thing I want to do is plot my bias line. So let's make some room here, and we'll do that. And here we go. All right, remember we're going to start by creating this little table where we choose convenient values of VGK and find the resulting plate current values. And remember, I sub P equals negative VGK divided by RK. So The one I like to start with is VGK equals 0 volts. That gives me 0 milliamps plate current. That's right down here at the origin. And the second value here, let's use this VGK equals negative 20 volt curve. That's one right here. So if we set VGK to negative 20 volts, we'll have a resulting plate current of about 35.7 milliamps. So we're going to have one point here at the origin. We'll find our second point at 35.7 milliamps and plot our bias line. All right, I'm going to change my color to green here, and we'll plot this line going from the origin to the minus 20 volt VGK curve at 35.7 milliamps. That's right about here. And keep in mind, we're kind of eyeballing things here a bit. We don't exactly have 64-bit resolution. So if you're doing this at home, your results may vary a little bit from mine, and that's perfectly okay. Now, let's stop here for a second and think about what we've got going on. We've got our bias line here, and since we know that VPKQ is about 250 volts, that's right about here. If we come straight up from there, our Q point is located here. Now, that's pretty darn close to 10, 20, 30 milliamps. So let's just say that IPQ is approximately 30 milliamps, and we know that VPK Q is approximately equal to VPP, which is 250 volts. So now we can find PDQ, the power dissipation of the tube at the Q point, and PDQ is equal to VPK Q times I sub PQ. So 250 volts times 30 milliamps is a PDQ value of 7.5 watts. Now remember, the maximum power that we can transfer to our load from this amplifier is half of PDQ, so the absolute maximum we could get out here is 7.5 watts divided by 2, and that's PO max theoretically is 3.75 watts. So whatever we get for the rest of our analysis, the power out is going to be something a little bit less than 3.75 watts. Now, if this is a pretty well-designed amplifier, our actual maximum output power should be close to this. But if it's not a good design, if something happened and we screwed up designing this, it's always possible for us to have a PO max way less than the theoretical maximum value. But that's why we're doing this analysis. We want to see how things work out. So the next step is going to be plotting our AC load line. So let's clear off our workspace again and get to work on that. Let's start by finding IP sat, and that is IPQ plus VPKQ divided by R prime L. So we've got 30 milliamps plus 250 volts divided by, that was 8.2 k ohms. And that gives us 30 milliamps plus 30 milliamps, which is 60 milliamps. And that's good because what we'd like is a Q point that's centered on our AC load line. So if we're sitting at IPQ of 30 milliamps and IP sat is 60 milliamps, that means we're centered on the AC load line. And that's as good as it gets. Now, we could just use proportionality and assume that because IP sat is twice IPQ, then VPK cutoff is twice VPKQ, so it should be 500 volts. But let's just go ahead and calculate it to make sure everything's cool. So VPK cutoff is equal to VPKQ plus IPQ IPQ times R prime L. So we've got 250 volts plus 30 milliamps times 8.2 k ohms, and that gives us 250 volts plus 246 volts. That's pretty darn close to 250. So we've got a VPK cutoff is, let's just call it 500 volts. It's close enough. So we're out here, and if we connect these, we'll change our color to red, going from 60 milliamps over here to 500 volts. And notice that our AC load line does go right through the Q point that we predicted based on our vertical DC load line. So everything is consistent, and that's what we're after here, to make sure that when we plot all these lines and points, everything works out the way it's supposed to. Coming up from here, this is our Q point. So we're all good. Everything looks great. I placed a purple dot here at our Q point location just to make it stand out better. And let me mark my VPK Q value here of 250 volts. And next, let's determine our output compliance based on plate voltage swing. Okay, so we're working here from 250 volts in the positive direction of roughly 250 volts. Okay, it's actually 246 IPQ times R prime L, but we could call it 250 volts. So our maximum positive swing at our plate is plus 250 volts. Moving in the negative direction, remember normally we would stop here at the VGK equals 0 curve. That's right about here at about 125 volts. So our negative swing based on hitting VGK equals 0 is negative 125 volts. Now I'm going to record these values over here as V prime out max, and I'm using a prime because it's the voltage swing at the plate we're looking at, not necessarily at the load. V prime O max equals 250 volts. V prime out minimum is negative 125 volts, and the actual output voltage is going to be these values multiplied by the reciprocal of the turns ratio. So VO max is equal to V prime O max times the reciprocal NS over NP. So it's 250 volts times 1 over 32, which is about 7.8 volts. VO min is equal to V prime O min times 1 over, NS over NP. So that's negative 125 volts times 1 over 32, which is about negative 3.9 volts. Now, if we could move our operating point all the way over to the axis, we'd get a swing of negative 250 volts, but we can't do that. We could swing the grid positive, but the plate voltage is going to stop at minus 125. All right, next, let's determine the voltage gain. So let me clear off the workspace. And we'll start by determining the gain of the tube at the plate with respect to the grid. That is, AV equals GM times R prime P, but I'm going to put a prime on the voltage gain as well because that's the gain of the tube, not necessarily the overall gain of the amplifier. Our transconductance is 5 millimos, and little rp, if you recall, is equal to 1.6 k ohms. So that gives our tube a gain of 8. That is, the plate will change by a factor of 8 with respect to the grid voltage. But the actual voltage gain is going to be AV equals A prime V times the reciprocal of the turns ratio, because we have a step-down transformer, so that's NS over NP. And our actual gain then is 8 times 1 over 32, which is 0.25. So we've got a very low voltage gain overall, and that's not too surprising because we have a relatively low mu tube. Mu is only 9.8, and we know the gain of the tube is going to be less than that. It's 8. And overall, we're stepping down by a factor of 32, so we get a pretty low voltage gain. Finally, we're going to determine the maximum unclipped output power, and I should have recorded my clipping points over here because we're going to need those. If you'll recall, our maximum output voltage was 7.8 volts, and our minimum was minus 3.9 volts. And we're going to use the lesser of these two in magnitude because, remember, we're going to clip first in this direction, moving our operating point to the left. So PO max unclipped is equal to, in this case, VO min squared divided by RL. So that's going to be negative 3.9, but since we're squaring, we'll just leave out the minus sign. 3.9 volts squared divided by 8 ohms, which is about 2 watts peak. We want the RMS value, so P out RMS is equal to PO max divided by 2 for a sine wave. So 2 watts divided by 2 is 1 watt RMS. And there's our maximum unclipped output power, 1 watt RMS to the load. Now, if we could swing our operating point all the way over to the left, we'd get an output power of substantially more, about 3.7 watts, but we can't do that. We could swing the grid to a positive value, but the Q point is going to stop here at the VGK equals 0 volt line. All right, so I've consolidated all this stuff into a nice, neat version over here, and you want to take a second to look this over, screenshot it or whatever, and now let's go on over and wrap things up. I'm going to leave you, whoops, let me try that again. I'm going to leave you with a homework problem. And this time we're using an EL84, which is somewhat similar to a 6V6. Our power supply voltage is 200 volts. Turns ratio this time is 18, and we're using a 16 ohm speaker. Here are the curves for the EL84 in the triode mode. And just figure out everything that you can figure out for this circuit, and we'll go over that in the next video. All right, I'll see you next time.